Waiting for the recording. Welcome, everybody, to this week's installment of the California Dreams Technical Seminar Series. Um, the UCSB Nanofab is one of the great resources we have in Southern California, a demonstration of the really good work that a nanofab can do, and a nanofab that operates sustainably. We are very glad to have them in our hub. And one of the reasons that nanofab operates so well is because of Demis and people like Demis. The culture in the UCSB Nanofab is just great and makes it a very productive place for users to operate. And we've been very lucky to have Demis part of our California Dreams activities from the beginning. Demis contributes to workforce development as well as the technical nanofab capabilities that we're going to hear about today. Demis graduated with his Ph.D. from UCSB and in Blumenthal's group in 2012, where he worked on creating ultra-low-loss optical waveguides, and also worked with the John Bowers research group there at UCSB. After he graduated, he worked at Praevium Research. I'm not sure if I'm pronouncing that right, developing near-infrared and mid-infrared tunable semiconductor lasers for medical imaging and gas spectroscopy, respectively. He's been working in the nanofab at UCSB since 2006, but he's currently the manager of the process group in the nanofab and is knowledgeable about fabrication techniques, troubleshooting processing issues, materials characterizations, developing new repeatable procedures for fabricating devices, and I might say everything that goes on in the nanofab lab there. So we're very glad to have Demis speaking today, and I'll turn it over to him.
Thank you very much, Steve, and thank you everyone for attending. That's right, my name is Demis John, work here at the UCSB Nanofab, and the last part that Steve mentioned there, the helping people make repeatable and scalable processes, will be what we're going to be talking about today. So I think some of you are probably familiar with the Nanofab, but just in case you're not, this is our mission. At the UCSB Nanofab, actually, the lab was launched by Jack, in part with Jack Whaley, and one of his missions was to make it as easy as possible for companies to access, which is sometimes considered a bit of an unusual mission for a university lab. So translation, this part of the research and translation mission here, has always been a core part of the mission. And that also, I should point out, has been strongly supported by very entrepreneurial professors here at UCSB, many of whom came from Bell Labs. So that's kind of our core mission, right? Supporting research, but also industry success. Just an example of where we fit in to the ecosystem, right? We have advanced semiconductor R&D. That's, for example, our research groups. We also have small businesses. And this is kind of what we think the translation looks like. We have 22 staff in our nanofab. For those of you that don't know, we're also opening a new lab called the ProtoFab, or prototyping facility. You can see the website there. So for taking your microchips and actually getting them to real prototyping status. But so how do either of these work? We're not a commercial foundry, right? So when people think about a fab, they're usually thinking about massive silicon CMOS foundries. We don't have any PDKs. So instead, we make as much information as we can possible. I'll talk about that later in the presentation here about why that's important. You can almost think of us as a makerspace or hackerspace for making microchips. We train people, we make the equipment available, and you come in with your own designs, right? We did not design your laser. You're going to come in and make your laser or your circuit, and that means we actually have to support a very high mix, right? So the question is, how do you support that high mix? And we do operate in the black, sustainable entirely by revenue from people accessing the lab, right? So the high mix is almost like think of it as diversifying your market, right? We have high use through that high mix. So how do you do high mix and scalable fabrication when you're coming from a silicon CMOS fab? I think it's very common that people think those are not compatible, right? So obviously a lot of R&D and invention here, and but we're also trying to support industry at the same time. And again, I don't think it's the question is how do you put both of these in the same lab at the same time, right? So what does the small business success look like, right? Different from academic success, right? Academics need to publish papers, demonstrate first initial prototypes or proof of principle, right? And in industry, they might be looking for something different, right? Their success, if they are a success, they probably stop using our lab, right? That's a success story for us. So they either build their own fab, or they get acquired, or they work with someone else that uses a foundry. We've seen all of the above. Okay, so that's kind of like the model we're going after. You've probably seen some of these companies. These are just some examples of the commercial successes from our lab. You've heard of some of these, kind of a smattering of different technologies. I think again, we want to look at the high mix aspect of these different technologies, right? All the way from mirrors, extremely high reflectivity mirrors for sort of fundamental physics applications, quantum computing, and out to infrared cameras and even flashlights, right? So all the different many different types of technologies, right? So again, this is just an example of the high mix, and even to give you an example of sort of all the different types of technologies, these bolded companies, this is a list of all the companies that have used our lab. The bold ones specifically are spinouts from, related to UCSB somehow. Okay, so all that just to show high industry usage. And you'll see, for example, if you extend that to the entire country, this is an example of the academic and industrial users from around the country or from around California. And you can see here our the number of users is approximately 50-50 industry on the top here and academic here. This is data from since 2006, but if you look at just the last 5 years, 52 startups. In just July through December 2025, we had 22 startups. Actually, when I showed Brian Thibault these numbers, he said, that can't be right. So I had to pull up the spreadsheet, and he looked and goes, oh, that is right. We were surprised by those numbers as well. So I run the process group here at the Nanofab, and our mission is to ensure lab users are getting good results. It's a very simple mission, but this word results is a loaded term because if you're an academic, your result could be you need a plot for a paper showing some variation, or you need a first ever proof of concept device that no one's ever made before. Whereas if you're a company, you might need something, you have technicians in the lab, and you have your results are that the process works the same every week, or we varied only one thing. But regardless of whether you're academic or industry, one of the key things you really care about in terms of this is that you're getting results fast. They both want to get to the end fast, right? So one of the key things that my group does is to make sure we know our customers, because my staff operates basically like lab users. We're in there in the lab doing remote fabrication services or doing process calibrations or all of the above, and really using the equipment, right? And part of that culture that Steve mentioned is we're all trying to get to the end really quickly and then iterate. So this presentation will be about the key things we find we have to teach to industrial and academic users, academic users, how to achieve success and good results quickly. I could also have titled this talk, All the Things I've Learned from Brian Thibault and the Nanofab staff since 2006. So these, it's maybe a little bit of less of a technical talk. And again, maybe addresses some of the culture that Steve mentioned that we have here at the Nanofab. So what are the critical ways of thinking about scalability? So this is kind of an outline. Typically in educational institutions, by the way, we are an educational institution. This is true for every other university Nanofab. And I think sometimes we don't necessarily appreciate that your staff, your Nanofab and machine shop or materials analysis staff are also educators, right? They're at an educational institution. And so education, academic groups, may operate under this kind of, I just need one to work. We're also going to talk about how do you then go to fast R&D cycle, and a key aspect of that I find I have to teach all the time is over-engineering or de-engineering. So how do you figure out how to not solve a problem? It's my favorite engineering solution. And then lastly, the scientific method in real-world manufacturing. So some of this, is taught in classes, and yet I find that these are some of the things that we have to kind of teach a lot here. So let's think about education in an R&D fab, right? So one way, as a key way of thinking that I think is helpful, is to redefine fabrication. Microfabrication, nanofabrication is literally just machining. It is the most advanced machining in the world, but it is machining smaller than you can get with a drill bit. So what is useful about thinking of it as machining? It means that you can use all the same thought processes that a metal machining shop does, for example. So, for example, a CNC mill at a metal machine shop versus stamping versus electroforming. These are all very different types of metalworking. What's different about those? Why would you pick one versus the other? So, if you add one more to that, what's different about microfabrication? So, for this type of machining, for microfabrication, it's the type of machining that gets you atomic level control. I mean, we do it all the time. You literally type in 20 atoms, 20 angstroms into a tool, hit start, and wait 5 minutes, and you got 20 atoms. It's kind of easy. And then also, how do you do this at scale? So at scale, what that looks like for us for this type of machining is, unlike a CNC where you put in a block of metal and it's machining one part at a time. For us, all the tools are set up so that every single step touches 100 or thousands of chips at the same time. Right, so that's how you do scale, right? Same amount of time to use the tool, but if you made 1,000 chips for that one step, you just divided the cost by 1,000, right? So that's just how you do atomic level control at scale. That's what's special about this type of machining. Now, in the academic world, we often have this saying, we just need one to work and then I can graduate, which really is true in some sense, right? It depends on what your research is. If you're making a brand new type of device, never made before, a real publishable result could be one working device, right? Because what your goal is a proof of concept that the idea works. We're doing a new type of quantum well or a new type of material. Is this even, a useful idea, right? So the proof of concept really, you might only need one to work. However, in practice, what does a researcher and a company actually need? They generally need to make plots. So for example, if you look at this again, laser, for example, you can see here variation in the length of a laser, for example, so that you can make a plot and calculate your efficiency, your quantum well efficiency, for example, or your mirror loss. Or similar here, if you're making a new type of waveguide, you might need to vary the waveguide width and you actually need to make plots. So actually, if you just got one to work, only one of these lasers or one of these waveguides, you can't make your plot. So even in research and R&D, you actually do care about uniformity and yield. Okay. On the other, secondly, after you have made your plot, whether you're at a company, you finish your chip, you go back to the lab, and you do testing, and you respin a new design. Right, you're going to come back 1 or 2 months later or longer, and then you want to do another fab run, and you're only going to, let's say it's a 10-layer fab run, you're only going to vary 1 or 2 layers out of that. Everything else is going to be frozen. So actually, you do care that 2 months later you come back and you do not have to redevelop the entire process, right? Your lithography should still work. Your etches should basically be the same. You want to do research on just 1 or 2 layers out of this that you're going to change in your design. Okay. So again, even though it may be true that we just need one to work, in practice, you do need uniformity and yield, and you do need repeatability in a university lab, both in academic and industry support. So scalability and repeatability are actually linked, right? So if you want to go to scale ever, that means that is thinking about repeatability. So all of these really do play into this idea of scalability. This is why we're doing this type of manufacturing. So what that might mean, for example, as part of the culture as an academic, for example, it's really important, I think, that we have academics and companies working side by side. When I was a graduate student here in the Nanofab, I learned so much just because of the fact that I'm working right next to companies and their way of thinking, is infective, right? Like I learned those ways of thinking. So for example, if I'm sitting there in the lab and I think, okay, I have a mistake on my mask, or how am I going to get this fab to work? Oh, well, I could grab my tweezer and I could poke every single device one by one, and then they would work, like, scratch off some metal or something like that, right? Even though that's technically an option to get one to work, the culture of thinking about scalability, even if you're not going to actually do scale in your academic research, thinking about, is this scalable, means, you know what, I'm not even going to try that method. Instead, I'm going to go back to the lab and find a method that is really scalable. It uses lithography. It touches 1,000 devices at the same time, right? So come up with a way that uses wafer scale methods. It's just built into the culture. And then the second part that you really are teaching grad students, but also, honestly, I've also had to work with industry partners on this, is how do we do fast R&D cycle, right? So one key important aspect there is that the first run is always the hardest. Okay, so let me give you an example of that. So when you do a first run, your first ever run, for example, I had made silicon nitride waveguides here, and it sounded easy. It was, there was papers on this, but I was the first one to ever make it here at UCSB, right? And the first run means you are not only doing simulations from the ground up, had to write your own simulation tools, then you're doing your first ever mass design, and then the long part in the fab is that you're starting with no instructions. You're starting with no traveler. You're guessing, you do your best, you have expertise you can pull from, but really you're writing these work instructions for the first time ever. So getting through all these steps, the first time takes a long time. You got to learn all the tools. You got to make instructions. You got to fix things that were wrong. But more importantly, you also want to go to the testing lab, plug in your chip, and actually test it, which means you got to go there and actually set up the whole test. The test itself as a whole, could be a month's worth of just setting up the test and getting a result, right? So really getting to the end of this cycle one time takes the longest. The end including test results so that I can iterate fast, right? The important part is that once you've done this once, the second run takes 50% of the time, and the third one takes 25% of the time. So really, the learning for all of these steps is the longest part. That's both at a company or in the academic lab, right? So you really want to get to the end fast, and then iterate many times before you graduate, or at a company, get to the end fast and iterate so that you can find your right design, right? So fabrication development is slow and long, and really, if you have to go and spend a lot of time developing some step, you really want to avoid that if possible. However, you are doing something new that no one's ever done before. That's both at a company. Your company is the only company in the world that does this particular chip. That's why you launched, right? So at some point, you're going to hit something that is confusing, critical, and you literally don't understand how this thing works. Then you do need to stop and really do the science. Okay, so I'll talk about that a little bit more, what that looks like. Okay, so what we found for really making this work is that basically you want to use available repeatable processes that are already developed and, most importantly, are documented well. So that's why you see our UCSB Nanofab wiki has tons of information of all the documented processes, right? And we've actually found that staff has to do some amount of this. I'll talk about this towards the end of the presentation here. Some amount of the actual development so that users can decide, should I go do the science or can I just get to the end fast? Okay. And then lastly, is my MacGyver solution scalable or repeatable? And if it's not, then I need to stop and I need to do the science. So let's look at what actually doing, quote unquote, doing the science looks like here. So I have found of years of advising all these different, academic and industrial users, one-on-one, in person, that I found that a lot of what I'm teaching is actually the scientific method. So if you reframe much of what our culture is, it's really how do you employ the scientific method in manufacturing? So I'm just going to give you some examples. There are so many other examples, but let me just give you an example here. So this is a very common statement. You probably will hear this in industry as well, in an industry fab, but definitely you hear this in academic fabs, right? Someone tries to do something, it doesn't work, and they say, okay, that tool just doesn't work. So how do they try and solve it? They rapidly switch to another tool that seems like it could do some similar process and see if it would just magically work. Okay, I'm not against this, actually. If you can, I fully support get to the end fast, right? If it turns out this doesn't magically work, then you got to do the science. So let me give you an example that came from an industrial user here in the lab. An industrial user that I might point out is extremely good at rapid R&D cycle, right? So they're using our masked lithoaligner, the MLA litho tool. They get in a misalignment and they're like, should we switch back to the contact or a stepper, right? So I just walk them through, let's use the scientific method here, okay? So let's turn your question into a hypothesis. The unspoken hypothesis that we talk about and negotiate and kind of come to is, I think the MLA misalignment is random and uncontrollable. Therefore, a second hypothesis, a different tool would not have such issues. These are both hypotheses that are not entirely true, right? Is the MLA misalignment random? And is it true that a second tool would not have such issues? Don't know. I mean, it could be true, right? Don't know. So let's test the random hypothesis first. Okay, how do I test this first hypothesis? This is the scientific method, right? Come up with a hypothesis, some forces you to state your assumptions, and then can I test it, right? So send me some photographs. Let's get some data to see, is it random? Not only send me photographs, let's get measurements of where on the wafer, and this is to test randomness. Is it actually random? So this is an example. I got 13 photographs like this by in a PowerPoint, all on separate slides. Here's my misalignment near the center of the sample. Here it is center left of sample. Here's it in the horizontal. I looked at 13 of these and I'm like, I cannot figure out if this is random from this data. So we walk back and say, okay, can you please plot this for me? Because we're looking to see, is there a pattern? Plot this for me, draw little arrows and put the numbers there. And as soon as we did this, actually, I did this plot for them. As soon as we did this, okay, it looks like it's not random. So just an example for this particular case, for example, get the data and test the hypothesis. Is it random? If it's random, these arrows should be pointing in random directions with different magnitudes. Since it's not, clearly we have a scaling. In this case, we clearly have a scaling or magnification problem. Next step, just to conclude this particular experiment. Next step, okay, go run the experiment again and take a photograph of the scaling value that the tool actually shows you. This has just turned out to be the problem. This tool does actually measure the scaling error, but by default, it is disabled, okay? Because it'll distort your CAD file, basically, during the lithography. So yeah, they actually did find that, turns out that scaling, did some quick math here. Yeah, that amount of scaling will lead to 2.5 microns of misalignment across the wafer, okay? So, this was like, 255 ppm of misalignment, 2.5 micron misalignment across a 1 centimeter piece, by the way, across a small piece. So key thing, how do you deal with, this level of scientific method? Just, okay, come up with a hypothesis. How do I test it? Test it with data. So bring me the data. And then you'll see that the other important part is really staff involvement in the process, and the equipment is really critical, both for academic and industrial, right? So, me or one of the other staff really knows how this tool works, understands how to think about alignment, and this is kind of what we're teaching these users, okay? So the institution, what we are is, you're keeping the institutional knowledge that we have here of how to think about these problems and understand how the tools work. It is the education in some ways as an educational institution for both industrial and academic. Okay. A second aspect of the scientific method is really working off of data. Okay, so one of my absolute favorite engineering solutions is to figure out how to not solve a problem. If you can figure out, don't even solve this problem, you saved yourself weeks of time, right? So this is actually my favorite type of engineering solution. So for example, a user comes in and asks, me and Brian deal with this very, very often. A user comes in and asks, how can I optimize my silicon deposition for improved uniformity, for example? I can visually see color changes and it looks bad. It's very eye-catching. So you can see the color changes across the wafer. So the next question is, well, okay, you're seeing a non-uniformity. How important is this for you to actually get a result? Remember my focus on results. So you have to kind of ask yourself, why am I doing this fab run? It depends on the user. It's my first attempt, so any result is a good result. If that's true, don't optimize anything. Or optimize really as little as possible. Like optimization is not important if you just need a first ever proof of principle, right? You can optimize afterwards, after you've proved that this even makes sense. And then you have some data to show that this is actually a limiting spec, for example, uniformity, okay? And then secondly, let's say, why am I doing this fab run is, okay, this is my third fab run and I really need this run to work for an upcoming deadline. Okay, that means there really is a performance spec. So, by the way, these are real world examples. So on this, my silicon wafer has really bad uniformity. I can see color changes across the wafer. How do I fix that? Okay, bring me data. So what does the data look like in this case? Do you have data or measurements from Fab Run 1 and 2, or simulation is actually data that shows that this level of non-uniformity will prevent you from getting a result? Okay, so it's just take your data and actually say, does this data really show I need to solve this problem? Again, I'm looking for the how can I not solve this problem solution answer. That's what I'm trying to figure out, right? Um, and you do need to minimize your risk, but not at the cost of adding lots of time. So you want to prove that there is really value in solving this problem. So, for example, optical simulations are very interesting. I did a lot of photonics myself, and so we'll do a lot of optical devices for remote fab customers. And so your question is actually, even if you have a simulation, is your simulation predictive of your actual performance? So an issue I have seen with multiple groups that we've worked with and done fab for is optical gratings. I found they're very often overspecified, and they usually overspecify the etch verticality. So, for example, an external academic customer, um, and an industrial customer said the same thing. Said, we need this etch to be 5 degrees max. If the etch comes out 5 degrees away from vertical, our optical transmission drops by 25%. Right, like we get way lower power out of the device. But then we went and looked back. I pulled up all the old fab data runs and looked at it and found, hey, we actually have etches that we did for you that were 15 degrees off, but you showed that there was good optical transmission. So it turns out your simulations are actually not that accurate. You need to feed this back into your simulation and refine it, right? So this maybe a key takeaway of that is, you really do want to question your assumptions. And the assumptions and specs often come from simulation tools. Again, it is real data, but you do want to confirm with data, is it actually accurate? So again, the key thing is always look for ways to avoid solving the problem. Again, because fabrication development is, long and hard. It can take weeks to figure out one of your 10 steps, right? Prove with data that you actually need to solve the problem. That includes questioning the assumptions coming from your simulation tools. And then lastly, I'm not going to go into big details of this, but if you can, if you're not sure, so in research, you literally might not know. If I ask, how bad is the uniformity? You might say, I really don't know, right? So can you devise a really quick, cheap, short loop to test a hypothesis or fail fast, right? So don't use your expensive epitaxy, don't do 10 layers. Can I just remake a wafer from scratch that only has 2 layers that in a week I can just test my hypothesis, do some quick optical measurement or some optical test to find out, do I need to solve this problem? Okay. This kind of stems from the idea of there's a quote I really like from Bill Gates. Bill Gates said, "I choose a lazy person to do a hard job because a lazy person will find an easy way to do it." So I think you can say I'm that lazy person. I'm trying to avoid doing the work and get to the end as fast as possible with minimum amount of effort, which it turns out is also good for both research and for running your startup company. Okay. Next, let's talk about another aspect of the scientific method in manufacturing, tolerance. This might sound really obvious. I think for anybody on this call that has done a lot of manufacturing, the idea of tolerance really, it's kind of second nature. But you'd be surprised how often I find I have to, me and Brian and our staff has to explain the idea of tolerance, both to academics, but also to industry engineers very often. Okay. And it's not just the idea of tolerance, right? You can learn the idea of tolerance in a class. Maybe you did it in engineering class. I think, and I had to learn this myself. I knew this name, did not know how to use it. So I think the difference is that when you actually come into the manufacturing world, when you're actually going to go do fab, what we haven't really learned is how to apply tolerance to my actual fab. So I think the problem of tolerance that I often run into stems from our use of PowerPoint, or in this case, FabuBlocks. So anyone who's done real fab will look at this PowerPoint and say, okay, I'm trying to make a chip with a silicon nitride membrane. Here's my silicon substrate. It's got some metal on top of it, right? What's the problem here? Everything's perfectly straight. Everything's 90 degrees. Nothing etched into another layer. Everything stops perfectly on the layer, right? It's just really non-physical. Sounds funny. I am trying to be funny, but I really do think we don't sometimes really have the imagination for where does manufacturing, real physical manufacturing, show up in this. So in real manufacturing, let's call it, CMOS fab or metal machining or even carpentry, people will specify a tolerance. This has to be 1 inch plus or minus, 5% or something like that. However, in CMOS or let's say circuit design or something like that, you probably get your tolerance from running many devices. You have a lot of statistics, right? You're just cranking out identical steps and identical fab runs and identical devices so much that you have statistics on both device performance and fabrication steps. So for R&D, it can be a little bit difficult, right? Have you ever done this fab before? If you've never done the fab before, you don't have any statistics and you kind of just need to try something. But we still want to think about the idea of tolerance when you're just going to try something. So for example, let me go into another example that comes from, again, I've seen this both in an industry user, but also from other academics. Okay, so here's an example. We have a very common mistake that I see, again, stemming from the use of PowerPoint in some ways, is I have an epitaxy stack, and I need to etch down to the contact layer, which is highly doped N plus, so that I can put metal on it and get electrical current into this layer, so it can go through the epi stack, for example, like a laser or something like that. Okay, so look at what they specified here. This literally happens. This happened just 3 weeks ago. Okay, I need a 921 nanometer etch. Not exactly. I mean, people will specify down to this. So for those of you that are experienced, we'll look at this and say, okay, I see the problems here. Right. One, if you think about your high school science class, you've given me a 1 nanometer tolerance. I think it's technically what that means. We have significant figures down to 1 nanometer, right? So I need to be within 1 nanometer. Do I really need 1 nanometer tolerance? Okay, so you might think, okay, Demis is being pedantic, right? Like, obviously they don't need 921 nanometers, fine. But the problem still stands. I actually really don't know what is acceptable to you. Like, what level should I tolerate? What's going to happen is my staff is going to do an etch, go measure something, and then we're going to be stuck. Is that acceptable? Okay. The second problem you see here is that your etch A is perfectly vertical and stops perfectly on this layer. Okay. So let's look at what that would actually look like when you put your real tolerance into the fab run here. So let's say I have, for example, in this case, for a dry etch, tolerance comes from etch rate. The etch rate is what can vary. So that means your error will be a percentage. Your etch rate goes up by 5% or down by 5%. So if you just add or subtract 5%, for example, from your target etch rate here, you can see we got two very different situations here. One of them, I'm not even touching my N plus layer, and the other one, I've gone into my N plus layer. Okay, so back to what is an acceptable result for the user? Now, the top one here, for example, is a complete disaster. You're going to end up putting metal onto a low doped layer, which means you're going to get Schottky contacts, and you'll get a very high resistance device. Whereas the bottom one will probably work pretty fine, right? So you can see that, again, this is a very common thing. People will specify etch to this depth. When I actually look at their epi layers, I say, I think you've specified the wrong thing, right? If you target 921 nanometers as a center point for my etch, there's a 50% chance that I get a really bad device, or half the wafer that had the lower etch rate is useless, and then only half of the wafer is useful, right? So obviously, how do you really fix this, right? I don't want 50% dead devices, right? Or half of my wafers are dead, for example, because of this resistive layer. So instead, you actually need to target, okay, anywhere inside this layer is acceptable, plus or minus 5%. This is really what we call design for manufacturing. It's always going to work, even if things go wrong. Now, from a research standpoint, you might say, well, should I stop in my in-gap layer or my gas layer? That'll probably have a difference in your resistivity, but I would consider that an optimization, right? So for example, for this particular customer, they'd never gotten an electrical device before. Getting any electrical contact is a huge result. Let's not solve the exactly which layer do we stop in. Let's stop anywhere in this layer. And that way, even if we're off by 10%, actually, it turns out it'll basically work, right? Second thing, are we talking about two takeaways here? Are we talking about percent error or absolute error? So you actually need to know your tools. So for example, I mentioned in a dry etch, your etch rate is what can vary. So therefore, we're talking about a percent error, right? As opposed to, for example, a CNC mill or a lathe, where the error might come from robotically positioning a drill bit. And that will have an absolute error positioning accuracy in meters, not in percent. So you really do need to kind of know your tools. How do I specify this error? But of course, that if you're doing an R&D device and you've never made this epi before, or you're in a lab that doesn't even have this etch, the real question is, what is my acceptable percent error? How do I design for manufacturing if I don't, unless I have to know what percent error should I expect? Is it plus or minus 5%? Is it plus or minus 10%? Right? And that really comes from your statistical process control. So some of you may have seen this in other slides, right? I think of this aspect of manufacturing as sort of like statistics analysis or noise analysis. If you're in a physics class or an engineering class, you're going to do noise and statistics. So kind of think of it like that. Those are the same ideas we're going to apply to manufacturing. Okay, so it's critical to understand your noise. You need to have process control data to even know what your tolerance, noise, and repeatability can be. So, for example, process control data. I'll show you some examples here. For example, so I can pull this over here for you. So here's the process control data we have at the Nanofab, run by an army of interns. I shall point out that we were able to double our number of interns because of DREAMS funding. So absolutely improved hugely by the DREAMS project, by California DREAMS. But you can see, for example, here are all the different tools. So here's one tool, here's another tool, and each tool actually has different films on it. Etching and deposition, right? So just to give you an example, we're generating statistical process control versus date with error bars for different metrologies, so deposition rate versus particle count, for example, for these particular tools. Okay, so so the question is, whoops, 1 second, get back to my slides here. So so you have to have that to even be able to know, is plus or minus 10% acceptable? So for example, over here you can see. Sorry, it's a little small. You can see, this particular tool is usually well within plus or minus 10%. So I could specify 2% on this particular fab run, for example, on this step. Secondly, this is this really statistical process control? These are just single steps, but in a real fab, you would actually measure device performance, right? You'd get all the way to measuring transistors or op amps or circuits, and you'd have correlation between device performance and single fab steps. We don't have that here at the Nanofab. I am not designing and measuring every single device. It's kind of up to the lab user to do their own SPC at that level. But what we're providing is, the single tool, a single step process control, right? So, for example, here, SiO2 etch data, for example, here you can see, plus or minus 10% is quote unquote normal. So that helps users know there's actually a very practical aspect of having this data that really helps in the lab is users would often come to us and say, hey, my etch came out bad, right? I think your tool is bad. And they could be correct, right? But I just need some data to show, is the tool bad? So this really shows, I can go to the plot and see, or ask an intern, hey, how did your last etch come out? Is it normal, right? And quote unquote, what is normal? Normal is only defined by what your historical data is. So we can see, okay, the tool looks good. And so, for example, we've had industry lab users come and say, hey, this academic user ran this weird etch. I think it messed up my etch. That's what's going on. And so thankfully, I had this data. We were able to pull it up and show, okay, actually looks like the tool didn't have some massive excursion. It could happen, right? The tool is not etching 50% low or something like that. And then actually, because we had this data and we know what quote unquote normal is, we can then actually have the user running a new etch, literally do a calibration run, get a data point, have the user run their etch, and then get another data point, do our calibration run again, and show, okay, yeah, actually their etch and their process did not cause our standard process to go way out of spec. So then the industrial user saw the data and said, oh, okay, like that was really useful data. They literally didn't know, is it the machine or is it something else? Now they know, okay, it's not the machine. And a week later, they came back to me and said, yeah, we looked elsewhere in the process and we found another step in our process that we had actually changed that caused that device to not work, right? So really, it helps with the politics in the lab. Bring data, right? Get out of the emotional state and being upset at someone and making hypothesis. That user messed up the tool. Data shows, yeah, okay, actually their process does not mess up the tool. You need to look elsewhere. Okay. However, this, for example, for an SiO2 etch, this is an extremely stable process, an extremely stable tool, right? is this representative of other users running other etches? So this particular tool, ICP2, this is actually a tool that has so many different etches in it: metals, 3,5s, oxides, all these different gases in it. So what we did kind of find is that SiO2 is a really stable etch. Generally, I mean, we've seen excursions and we catch them, but it's a really stable etch. So is that just because this etch is insensitive to any problems in the chamber? I know users are running sensitive etches. So we also set up a calibration process run by our army of interns, for example, for gallium arsenide. Okay, so this is a chlorine chemistry, the hypothesis being that it's actually much more sensitive to chamber condition, right? And so now at least we have data where staff or our users can go look at this. And you can see this is also plus or minus 10%. These are 5% error bars. That staff or users can go look at it and say, okay, is a chlorine etch still running, quote unquote, normally? Really what we found actually happens, although this data is available, you saw my website, it's got way too much data on it. I'm not sure that everyone knows where to go find the data they need. So really what happens is staff and our interns, we monitor these and catch when there's an excursion, or a user comes to us and we look at it and say, okay, did anything go wrong, right? So really staff involvement is important here. And just a quick aside, how do you get an army of interns to do this for you, right? What it used to look like was that we did have calibration processes for deposition, and really what happens, staff would run this 2 or 3 times per year at most, in between all the other things we were doing. And then for etch, we never ran these. A user would complain, and then we'd run a calibration etch and say, okay, is it good or bad, right? And measure all those kind of things. In 2020, we had 2 undergraduate interns. They had to be seniors with fab experience. And then in huge part because of the DREAMS funding, we were able to expand that to 6 interns. So no fab experience. We currently have 2 high schoolers in there, 2 community college students in there, right, across many different majors. And so now we went from, and you have to upgrade all your internal systems to be able to run an army of interns. You have to have really good tracking of your interns to be able to go to, a single point entry and automatic data plots, right? I just point this out because actually our interns now leave, and these interns are often either high schoolers or UCSB undergraduates in physics or chemical engineering or electrical engineering. They actually leave with an intuition for SPC because they've literally been plotting this for 6 months. So they know it never comes out like you expect. And then secondly, when something goes out of spec, when you get an excursion like this, they're working with my staff and the equipment engineers to see and operate on OCAP procedures, out of control action plans, and actually, hopefully see the films come back in spec, right? So the interns really get technician level experience where they just follow our instructions, data recording, filling out travelers. We have to correct them. Hey, you didn't fill out your travelers. Make sure you fill them out. Like, we kind of really train them on all those things, scheduling everything. It's really, really great experience for our interns. I tell them, I'm treating you like a technician so that you will be a better engineer one day. So when you ask someone to go take SEMs, you know that you just made them take 6 hours of SEMs and you owe them a beer. Last thing I'm going to talk about here is design of experiments. Again, these are terms just like tolerance. They're terms that we throw around and many people who are experts probably are aware of. But again, it is something that I find I have to, our staff has A, had to learn, and B, it's very useful to actually explain and walk lab users through. So again, I actually think of design of experiments as the scientific method in action, specifically in manufacturing. The DOE is how do you apply the scientific method when you're actually doing physical manufacturing? Okay, so again, it's actually still better to try and get to the end fast and don't do a DOE and don't develop any new fab process. But let's say you tried to get to the end fast, but it failed, and you found that you really don't understand why some step isn't working. Then you need to completely change gears, stop and do the science. And when you stop and do the science, don't do it halfway, because what you're actually trying to do here is you actually need to build understanding. Okay, the point of the scientific method is to actually build a real understanding of the underlying, invisible principles that are happening, right? So you tried to get to the end fast, it didn't work. Stop, slow down, and actually do a real scientific study. Okay, so if you need to do the science, then you do it fully. So and the point is that you don't have to do it again. Really develop a good understanding, and then you never have to do the DOA again. Okay. So I see this as there's basically 2 possible levels of design of experiments, 2 possible levels of DOE. There's one, which happens in research and companies, but definitely in research, is we don't understand this process at all. We got to build some understanding. So in this case, you don't even know what the knobs do. You don't even know what variables to change. Or you don't know how strong each variable is, right? So basically the two ways of handling this are the shotgun approach. You just try a bunch of different things and see if you can get some understanding. And then the more formalized one is the Taguchi method or L9 DOE. I'll show that here in a second. But you don't always have to do this, right? This is when you literally don't have an intuition for the trends, right? The other one is we basically understand the physics and we just need to modify or optimize it. So then you can just do a you could do a control and a single variable, a variation of analysis of variations method where you just change one or two variables at a time based on observed trends. This is the faster approach. So if you do actually have some physical understanding, some intuition based on data that you got from these kind of experiments, do this. Absolutely do this. Don't do this unless you are like lost in the weeds and you don't know where to go. Okay. The other important part of the scientific method is it forces you to write down your assumptions and forces you to record your results in a communicable way, right? So when you do a real DOE, one of the things that's really helpful is, your spreadsheet literally is hypothesis result. I measured, you come up with a hypothesis, you varied one variable, and then you measure it. Okay, so again, you can look back at it a year from now, or your graduate students or your next employees 5 years from now can pull that open and understand what happened. Okay, so let's look at, we already understand the physics and we just need to modify. Okay, so for example, I'm just going to quickly go through this. For example, this is actually a DREAMS project, fun, where we have an SiO2 etch, for example, and we're looking at because of our army of interns, we can see, wow, we've got more than 10% variation in our etch rate. How do we improve the repeatability of this etch? How do I get down to 5% variation in this etch, right? So we understand the physics, right? You can see all my little descriptions of what does this gas do? What does the pressure do? How does ICP and substrate bias work? So in this case, we do not need to do a Taguchi shotgun approach, right? Just change one variable at a time, right? This is what our interns are measuring. And just cutting to the end of this particular experiment, we tested single variables based on our understanding, and none of them reduced the percent error. So by one of my mentors in graduate school said, the scientific method can never tell you, yes, this is true. It can only tell you, no, those are not true. So in this case, we're sitting here eliminating single variables. None of these variables caused the error. So in eliminating all the obvious process variables forced us to look elsewhere. And we eventually identified metrology was actually the source of the error. It turns out that having interns who are kind of new to SEM, you can see the top surface is kind of blurry, right? Like interns actually drawing this line on an SEM was the major source of error, right? Okay, we figured that out by switching to ellipsometry. And we found that ellipsometry, which is curve fitting, so you've got like lots of data, you're doing real curve fitting. You can see we went from 10% error on our SPC charts to better than 5% error. I mean, these steps are us trying to solve problems, or you might have a sudden step because we changed a clamp or something like that. But essentially, the error, the SPC control, the process control, is better than 5%. So it turns out the process was actually extremely repeatable. It was our metrology that was the problem. Again, identified by going through a DOE and doing single variable or even two variable analysis because you have an intuition for it. On the other hand, I'm not going to go into details here, but this is something that we actually literally, Gopi, my staff, literally wrote a good tutorial on the wiki of how to use a Taguchi L9 DOE. So even setting up your array of experiments, this is, again, when you don't understand the physics, you're trying to build an intuition by looking at trends. This is the point. You don't even know what the knobs do, right? So for example, we did this for gallium nitride etching here and varied all the different variables. Even setting up your array is actually complicated. So we have to use an online calculator to figure out what are all the experiments we should run, right? And Taguchi is a way of each of these points, each of these plots, for example, is actually multiple variables changed. So that's why you can see, like, for example, over here, these error bars are actually very large. Because actually each three of these data points is actually changing. It's not just one variable changed. But you can see the error bars even potentially overlap, but you can get an idea of, okay, these are the basic trends. Okay, so it's kind of a way of minimizing your shotgun approach to just get some idea of what are the trends. So now you know the trends, and this doesn't give you your answer, by the way. You cannot do a one-to-one mapping of RF power to, for example, sidewall angle or etch rate. You cannot do a one-to-one mapping. But now you know the trends. You do the Taguchi method. Now you know, okay, I should pretty much ignore these flat lines. But this is, and for example, temperature. This is we can pick a temperature from this, for example, and then you go back and do your one-to-one mapping experiment. Okay, so this is again, because you don't want to go fast, right? So now you've developed an intuition, and now you can do a one-to-one map. So just to wrap that up, kind of a quick summary here. Lab users, they really want to make circuits and lasers. They don't really want to learn all the fabrication details. However, they're coming in there and making novel devices. So sometimes they're going to have to develop a novel understanding. You've got some material, you've got some etch or something like that no one's ever done before. So this basically this what I've from the DOE and these other principles, our staff basically provides the basic understanding. For example, maybe the staff does the ANOVA or L9 DOEs to give you, here are the trends, right? So that the lab users can get in there and just do the really quick, okay, we've got a kind of working process. The staff explained to me, this is how the fluorine etches it, and this is how the ICP power affects the trends. And then they can do their rapid changing a few variables ANOVA to get to a result really quickly, right? And then lastly, just as a summary real quick, yes, you might just need one to work as a proof of principle, even potentially for a company prototype, you just need one to work. However, even getting one to work, you really do need plots. So you do care about uniformity, repeatability, and even yield. You don't need 90% yield, but you probably need at least 50% yield or 40% yield, something like that. Lastly, you really, both for R&D and industry, you really want to focus on fast R&D cycle. And that means, one way I think about this is engineers love engineering. So we're going to over-engineer the problem. So instead, look at this. How can I not solve the problem? How do I don't solve the problem? Okay, to not solve the problem. Really valuable. And then lastly, we're really trying to apply the scientific method to real world manufacturing, right? So how do we get away from this tool is just bad and actually turn that into a hypothesis test? And then lastly, tolerance process control. This is thinking about like noise in your manufacturing process, and how do I deal with statistics? And then lastly, design of experiments. How do I generate, really what you're trying to do here is generate an intuition for what do the different knobs do so I can get to my result fast. So with that, I'd just like to thank the Dreams Hub for hosting this talk, and I'd be happy to take any questions.
Thank you, Dennis. That was a great talk. Watching for questions. You can put your hand up or put it in the Q&A. I'm going to start with a question while we wait for one from someone else. My question is one that can maybe be asked by a robot, because it's a question you can ask for almost any talk these days. You talked a little bit about, you talked broadly about analytics, but you made at least one specific reference to analytics. I don't know if I caught any references to generative AI and LLMs, but do you have thoughts about how those kinds of tools are likely to change some of these processes?
Yes, absolutely, right. Okay, I will tell you, AI has improved a lot over the last 3-5 years, but I'll tell you in 2022, 2023, I was typing in fabrication process questions into AI chatbots, and they were convincingly wrong, is what we all experienced, right? Where it sounded great, and then you look this up and you go, that's actually not a volatile product. That is completely incorrect, right? And why is that? We all know, hopefully many of the people on this call actually kind of have some intuition for how AI LLMs specifically really work. They're language models. They're not manufacturing fabrication models. They're language models, right? And they're entirely able to answer based on how much training data they have. So you can get an intuition for, okay, if I ask about a silicon etch, for example, maybe there's a lot of training data on that. But if I ask about a barium titanate etch with a thin film, bonded layer, how much training data is there on that, right? This is the core problem. So this is the question you have to ask yourself. Is there training data on that? And LLMs especially need thousands of, let's say, research papers or websites to be able to give you some sort of reasonable answer, right? So I'm certainly not against it, and I'm all for trying to improve it, actually. And I would love to, I think, part of the problem is that we just, we need um, in silicon CMOS, you get tons of training data, right? Because you're literally running, or again, you're running so many different identical processes, so you get a lot of training data, right? So yeah, it depends what you're asking, right? I think for big fabs, many people on this call might remember that UCSB, the Nanofab, we are running PDF solutions to do a lot of those analytics, and you see that there where we hit it head on, where we realize, okay, we have to build an intuition because we don't have enough training data for this to answer the question for us, for example. But absolutely opens up the door to, okay, if we can just run identical processes many, many times, then we can start to see trends and get training data. So actually, that's where the army of interns comes in. It turns out Nanofab staff are pretty much the only people that are going to run the same process every single day for years, right? A company coming to our lab is their entire goal is to not do that, right? They're doing the R&D here, and they're doing the repeat processes either in their own fab or in a foundry or something like that, right? So yeah, that's the short answer is ask the question if you know there's training data, or you have to generate the training data yourself. I don't think we're quite there yet, but I absolutely hope we get there. I don't think it'll be too long before even LLMs are able to answer kind of manufacturing questions intelligently.
Thank you. Who else has a question? I guess I don't see any. You must have been clear about everything you said. It was a great talk, very informative, easy to follow, and really appreciate sharing the insights and your partnership in California Dreams. And with that, Amy is going to share the QR code for the seminar series if you'd like to join future seminars. And then next week we will have Peter Westwick from USC. The week after that, Dimitrios Christodoulidis also from USC. And then a week off for the 4th of July holiday, and more information coming soon on what comes after that. So thank you one more time to Demis. It's a great talk. We really enjoyed it, and looking forward to continue working with you. And thanks to everybody for joining.
Thank you very much. Appreciate it.
Demis, before we go, I'm sorry. Oh, there was a comment. I thought it was a question, but great talk, Demis, from Mike Haney. Agreed.
Thanks, Mike. Appreciate it.
Okay. Thanks, everybody.